Okay, this is the first video on assignment number 42, and we're going to be looking at an introduction to logarithms, real basic. So inverse of an exponential function, y equals b to the x is a one-to-one function, so it has an inverse function called the logarithm of base b, or log base b of x. So let's go ahead and look at our basic parent function here of the exponential function b to the x. Recall that the table that we used to graph this was -1, 0, and 1. B to the minus 1 was 1 over b. B to the 0 is 1. B to the first power is b. The domain of an exponential is all real numbers. The range is all positive numbers. And this had a horizontal asymptote of y equals 0. Here I have graphed exponential growth, just as an example, b to the x power. The inverse function, f of inverse of x is equal to log base b of x. Okay. F inverse of x is equal to log base b of x, that's the inverse function. We'll muster x here, let's go ahead and fix this. And so let's go ahead and do our table. So x and log base b of x. And remember, when you're doing the inverse function, you switch the x and the y from the original function. So we have our table there, and all we got to do is switch our x and y. And that's how we graph logarithms also, is we do the exponential and switch the x and y. All right, so 1 over the base is going to be -1. Log base b of 1 over b is -1. Okay, log base b of 1 is 0. And log base b of b is going to be 1. Now your domain and your range are going to be switched from your original function. So the domain is going to be all positive numbers, so that does have a domain restriction. So later on when we look at finding restrictions of the logarithms, it's going to be very similar to finding restrictions of specifically square roots for us in this class. Okay, the range is going to be all positives. And instead of having a horizontal asymptote of y equals, we now have a vertical asymptote of x equals, and in this case x equals 0. And here is a rough sketch of what the logarithm of base b of x looks like. Okay. All right. So we're going to do some basics of the inverse properties, and then in the second video we'll get into how to go back and forth between the two forms, the exponential form and the logarithmic form. So let's go ahead and mention some stuff from that table. So log base b of 1 over b, we can rewrite that as log base b of b to the -1. And that ended up being -1. Okay, so you notice that the log base b and exponential base b are going to undo each other, and you're going to be left with the exponent. So that's an inverse property there. Log base b of 1 is going to be rewritten as log base b of b to the 0, and b to the 0 is 1, and so that's going to be equal to 0. Log base b of b we can rewrite as log base b of b to the first power, and that's going to be 1. So let's go ahead and write out our inverse properties here, and this is standard with any function and its inverse. We do the composition both ways. So the exponential inside the logarithm, so log base b of b to the x power is x, and then the logarithmic function of base b into the exponential function of base b. So we have b raised to the log base b of x. The exponential and the logarithm will undo each other, and so that'll be equal to x. Okay, so let's do a couple examples. And we're going to evaluate without a calculator. Just using their cancellation properties or inverse properties of exponentials and logarithms. So the first one we're going to look at is log base 6 of 36. And so what we need to do here is we need to rewrite 36 as a base of 6. So 6 squared is 36. So log base 6 of 6 squared. The base and the exponential of 6 are going to absorb, and so we're left with just the exponent of 2. For our second example, we're going to look at log base 4 of 64. So you might be thinking, oh, well, I know that 8 squared is 64, but that would be a base 8. So we have to do a little bit more investigation, and is 64 a power of 4? And it is. So this becomes log base 4 of 4 to the third power is 64. So the bases of 4 absorb, and we're left with 3. Okay, and our third example, we're going to look at log base 8 of 1 over 8. And so again, we want common bases of 8. So what we can do is rewrite log base 8 of 1/8. We rewrite the 1/8 as an 8 to the minus 1 power, and we just have to have a little bit of knowledge of our negative exponent rules. And so now we have the matching bases, so those will absorb, and we'll be left with the exponent of minus 1. Okay. Next one we're going to look at is log base 2 of 1/8. Okay. So now we have a different base to look at. Instead of base 8, we're going to look at base 2. So hopefully we recall that 8 is 2 to the third power. So log base 2 of 1/8 can be rewritten as log base 2 of 1 over 2 to the third power. Rewrite that as log base 2 of 2 to the negative 3, and that's using our exponent rules. So log base 2 of 2 to the negative 3, the bases are going to absorb, and so we're going to be left with the exponent of minus 3. Okay. And I think we'll sneak in one more example on this slide. So log base 9 of 9. Well, what's the exponent of the 9 there? It's a 1, so this can be rewritten as log base 9 of 9 to the first power, which is simply 1. Okay, we've got a couple more examples here. What do we got next? So now we're going to look at log base 3 of 1. Okay, so we got to be a little bit creative here and realize that 3 to the 0 power is 1. So we want to have matching bases here. So the base of the logarithm is 3, so we want the base of the exponential to be 3. So this will just give us the exponent of 0. All right, let's look at the next one. Log base 7 of the square root of 7. We can rewrite that as log base 7 of 7 to the 1/2 power. Remember, the square root is the same thing as the 1/2 power. Now we got the matching bases, so we will be left with the exponent of 1/2. Okay. All right, let's talk about something called common log. So on your calculator, you most likely have a log button. If you have a TI 30X2S, it's going to be right underneath the second button on the left-hand side, upper left-hand corner. Okay, log. So if we just see log by itself, it's understood that the base is 10. Kind of like when we say like x. X means 1x divided by 1 to the first power. So we don't usually write it there, but it's understood that x could mean 1x to the first power all over 1, just depending on what we need to do in that context. But when we say log, just regular log, no basis explicit there, we mean base 10. So log of x means log base 10 of x. So for example, if I wanted to simplify log of 1 million, I know that the base of the log is base 10. So is 1 million a power of 10? And the answer is yes, it's 10 to the 6th power. So now you have the bases matching up, so we're left with 6. Okay. All right, we got a little bit more to do. Almost done. Now we have E. E is a special number. We're going to see a lot of it in the last month of class here. E is called, and it looks like it's Euler, but it's pronounced Euler. This is Euler's number. And Euler's number is approximately 2.71. On your calculator, if you have a TI 30X2S, you have the second button on the upper left-hand corner. Underneath it is the log. Underneath it is the ln button. And then if you look above the ln button as the second function, you have e to the x. Okay. ln is the notation for logarithm of base e. Okay. So it's got its own special notation. I apologize if mine looks like an h. So it's ln, not h. So if you write it fast, it may look like an h. I know I'm guilty of doing that sometimes. But it's ln, not h. Okay, so ln of x is equal to log base e of x. So we got 2 more examples. So the natural log of e to the 5th, you got to think about that as what's the base of ln? It's e. So we have log base e of e to the 5th. And so our inverse properties will work this out to be 5. And one more. The natural log of the cube root of e. Remember the base of the natural log is e. And then cube root of e. Cube root is the same thing as the 1/3 exponent. Not 1/2, sorry about that. 1/3 exponent. And so when that simplifies, it is not 1/2, it is 1/3. Okay. All right, so this is going to be the longer of the 2 videos. We'll see you in the next one.